very excited to share. And, maybe if there are areas for collaboration too, that would be great. Or a mentorship, insight, things like that. So let me know when it's okay, time to start, and I'll go ahead and start.
Sure, maybe let's wait for one.
Is it Lido or Lido? How do you pronounce it?
Lydell. Yep, that's
Lido.
right.
Okay. Yeah, very interesting topic. Look forward to your talk.
Absolutely.
Idea.
Listen to a few of your talks as well, and I appreciate your mindset. I like a lot of your ideas. So I'd be happy to get your insight and mentorship. After you hear what I have to say. Yeah,
Thank you. Much appreciated. And like I say, look forward to your talk.
awesome. Yeah, thank you very much. How long has this meetup been in existence? How long have you guys been meeting, doing events like this?
8 years.
Oh, that's beautiful. That's beautiful.
Yes.
And are there other I guess sister meetups? Like this is the DC. Are there other ones that are, I guess, across the state, or is there any like structure or relationship to other meetup events?
We're independent, but I know there's a Chicago meetup from Dr. Barry Bird, and Dr. Barry Bird is online, and maybe Dr. Bird can talk about it.
Awesome.
Yes, it's a Chicago meetup. Yeah.
Our next meetup up is, when is it? Let me just check. We have one this month. Let me look for it. There it is, training neural networks on quantum computers. Thursday, the 18th of September. Dr. Leibowitz.
Awesome.
If you look for Chicago, Quantum Computing, Chicago, Illinois, and beyond on Meetup, you'll find it and be able to register for our wonderful session.
That's great. Hey, thank you. Yeah,
Okay.
even before coming to this, I'm a believer of prayer, and I've been praying for a meet with I guess I could call us nerds, or people who are hyper focused on this topic, just to be able to share and learn and be in that ecosystem. So this is for me, this is a pretty awesome opportunity.
If you want nerds, we got them.
That's right. That's right. Good stuff.
And if you have some more topic, we welcome you to come back in 2026.
Awesome. Okay. Yep. That would be great. Yep. I'll talk a little bit about, I'm looking for funding as a startup company. So, happy to maybe talk about that and, yeah, continue this effort. That would be great. Have something to talk about then for sure if funding comes through.
Sure. So it's a 1 past 3. So we have about 20 people online.
Okay.
So let's start it. So let me hit the record button. Hello, everyone. Good afternoon, and welcome Lindell Aaron to be our speaker. So that's all yours.
Awesome. Hey, thank you very much. Hello, everyone. I'm going to go ahead and share my screen. My name is Lydell. I'm a CEO or a technical co-founder at Collective. And at Collective, there's a mission, but today, here's what we're going to talk about. I'm a single member startup, and I've been working and very interested in quantum computation. I'm an independent thinker, so I often, take a circuitous route to get to the same answer that maybe industry is looking at. So in other words, these are some independent ideas in quantum that I've been taking, and but I've also been learning the traditional quantum too. I wouldn't call it traditional, the contemporary, reading books and coming up to speed and seeing how these ideas might fit into the existing framework. So today I'm going to talk to you about a technique I've looked at called factoring with waves. And it's a frequency phase perspective on quantum computation. And so, yeah, I'm happy to be here, and I look forward to hearing your feedback, mentorship, like, hey, go look at this, go look at that, go talk to these people. Any feedback like that would be great. So I founded Collective Autonomous Systems in 2019. We're a registered company in California. I still have a small office in Escondido where I do, have our registered business there. And our goal is to build systems that help us live in a sustainable relationship with ourselves. Often we humans can be our own biggest hurdles, our own biggest problems. We can create the problems that we ultimately end up solving. So that's kind of an interesting theme that I thought would play well into the technology that we're developing now. So two technology areas that we're in is working on a jam-resistant drone data link and a survivable drone, and quantum computing. So this quantum part is considered a moonshot, but we do have a patent pending, and it's published right now by the USPTO. Of course, patents don't mean anything unless you put sweat and tears behind them and you put effort behind them. So I've been working on that now, and this talk is a bit of that too. Today, here's an outline of what we'll talk about today. I want to describe or share with you a physical property of integers, because that's how this started. I thought, how could I, literally brainstorming session thinking, how can I think of a number in a way that could be factored, and so I sat down with some, a graphing calculator, and I just try to re-envision how I look at numbers to exploit the physics of the natural physics of numbers. So I'll share that with you. We'll talk about some zero crossing detection, how that plays a big part of this approach that I'm going to share with you. And then how when you factorize a number, there's a sort of user interface that you can quickly display that result, and I'll share that with you. I'm going to link these three bullets, the first three bullets, with the discrete Fourier transform. You all might know it as the FFT. That's a popular fast implementation of the discrete Fourier transform and how that shows us a frequency spectrum. We'll talk about the role of precision in zero crossing detection. How you can get more and more precise with your zero. If you can get more and more precise with your zero crossing detections, you can factor larger and larger numbers. And so there's a bit of a Moore's law there, whereas Moore's law was shrinking of shrinking of what can go on a transistor. This is more of increasing precision and how that can lead to factorizing larger and larger numbers. We'll talk about the quantum state as a mode of oscillation. That's how I've been treating it. And then I'll share with you on line 7 for all the tinkers out there, such as myself. I often think, man, how can I build one of these things in my at my desk? How can I build a quantum? So we'll talk about what's the minimum viable product to build what I described. In number 8, and we'll talk about the quantum advantage. There's a little chart that shows how classical computers factor numbers and how a quantum, this implementation might factor numbers in that same time. And there's a break-even point, and I'll talk about that. And then lastly, we'll talk about some other applications of it. We'll talk about wavelet switched networking. That's what I've been calling it, and I'll explain why I call it wavelet switched. And then we'll talk about one other application this is in the application, the USPTO application, but which is modeling of reactions. How we can do. I've been calling it reactive computing, because it's not computing based on the fetch and store architecture of modern digital computers, but it's an architecture based on resonance, of computing resonance and detecting of wave functions and things like that. So let's start out. If you were just to start with a graphing calculator and think about numbers, often we think of numbers as bits. I mean, in the computer, they're bits, ones and zeros. I have background in computer engineering. My degree is in computer engineering, so I am a computer nerd. But I thought, okay, we're using bits today. We're using transistors and switches. But if I could think of another way to represent a number, what would it look like? And I thought about an oscillator. I'd represent a number as a mode of oscillation. And so that's exactly what I did. I started out by representing numbers, uh, integers as modes of oscillation. So for example, you might have a sinusoid of 1 hertz. And if we look at number theory, every number, whether prime or every number is prime or composite, and every prime, even prime numbers are divisible by 1. So of course we have in this architecture an oscillator at 1 hertz, and that serves a lot of purposes. One of them being a synchronization. So we synchronize to the 1 hertz sinusoid. All the other sinusoids in this architecture are synced to the 1 hertz because they're divisible by it. So there's this really interesting physics that happens where in this picture here, you have a dark 1 hertz wave. And then I also overlaid a 2 hertz blue dotted line, and you can see how that overlays. Now this picture, the architecture only needs to go between 0 and 2 pi, right? One full cycle relative to a 1 hertz wave. So you can see that we're only doing 1 hertz, or 2 pi of a 1 hertz wave. But then we can also overlay the 2 hertz sinusoid. And then what I also did is I overlaid a 16 hertz sinusoid. And this is just an example. And so if you look at the zero crossings, what a zero crossing is where the sinusoid crosses the 0 reference, and you look at the upward going slope, you can see that there's a natural, that the factors, the common factors become visible. For example, the 16 hertz wave is here, and you can see I've outlined where that 2 hertz wave also crosses 0 with the 16 hertz wave. So there's this bit of resonance that can, if you're using zero crossing, and I'll show you some more examples where if you treat numbers as modes of frequency oscillations, and you look at them as sine waves, and you perform zero crossing detection, you can detect the factors of a number. So this is one picture showing 1 hertz and 2 hertz, 1 hertz, 2 hertz, and 16 hertz overlaid. And the red dotted line is the 16 hertz. Okay. In another example, you can see in this next example, I have 1, 3, 5, and 7 hertz. And I also overlaid 21 hertz, looking for divisibility between, is 1 divisible by 21? Yeah, it does happen to be, but 1 is not interesting. It's just synchronization. It's divisible by, 1 divides everything. But when we look at 3, 5, and 27, we can see that 5, there are no matching zero crossings with 5, but there are with 3 and with 7. So I know this chart is a little bit hard to read, so we'll have some other pictures a little bit later. And that's what the computer is going to do for us. We're not going to have to keep track of these zero crossings. We're going to leverage a special computer to tell us when we have a resonance, a match in resonance. And that's why I call it, instead of computing the factors in digital computing, we'd say we're computing the factors of a number. In this approach, in this computing, we're detecting the factors of a number. So there's no traditional like dividing, trial division or whatever algorithm you might have. It's really a physics detection type of concept. I have a few of these examples. Here's another one with 5 and 25 hertz. So you can see at these 5 hertz modes, 1, 2, 3, 4, 5. That, if you look really hard, I know the color is a little hard to see, but you'll see that the 25 hertz, which is the blue sinusoid, it crosses 0 at the same point as the 5 hertz wave, and not with the 3 hertz wave. or the 7 hertz wave or the other wave. So you can kind of rule, you can look at factorizations. Here's another example with 1 hertz. It's showing 2, 3, 5, 7, 11, and 23. So I wanted to show 23 and look for, just, so what I did in rethinking numbers is I just did a few small examples looking to see, is it true that if you have a number, and we'll call that the dividend, the number you're trying to divide, such as 1,000 or 1,001, if you were to overlay that with specially, ultra precise oscillators that were ultra precise, coherent in phase, you could line them up in phase. Could that really, tell you divisibility? Like that was a question. So I played, as you can see, I played with these numbers, these smaller numbers, just to get an idea if it was possible. Okay. And what you want to do is you're going to have a zero crossing detection. And these zero crossings, this next slide illustrates what it might look like. Now, maybe later at the end of closer to the end of the talk, I can show you like a live demonstration, like a model. But what you're seeing here is you're seeing 1 hertz, 3 hertz, 2 and 5 hertz, all overlaid. So 1, 2, 3, and 5, all prime numbers. As you might have known, these are all prime numbers. And what we're looking for is that moment that the wave crosses 0 on the upward slope. You can choose, you can have an architecture that goes on the downward slope, but you have to be consistent. So we're looking at the upward slopes, and wherever you see that upward slope or downward slope, we're producing a pulse. Now this is zoomed out a little bit far, so the pulses look very sharp. Right, so if you could imagine, if you can see, let's take one. So, right, there's 1 hertz, it's going down, and then there's a downward going pulse, and then it goes back up, and there's an upward pulse. With 2 hertz, we have the red line. I know it's a little hard to see, it gets a little busy. There's a downward slope, an upward slope, a downward slope, and an upward slope, right? So you're just doing a zero crossing detection, and you're generating these, what I call zero crossing detection pulses. Okay, so these pulses are a key, they're most important to this architecture working, the pulses. Now, there are some, I could probably go on a little more detail about the pulses themselves. They have to have certain special characteristics, and that's part of the engineering effort too. And part of me coming here and talking is, you guys might have some experience. Say, hey, I know an approach or whatnot. So that's always welcome. But these zero crossing detection pulses look like sharp waveforms overlaid with the sinusoids here. You can see the spikes there. Okay. And so what we have is we're using resonance. And when you do, in this case, I have a 15 hertz wave. In this example, I have the same 1, 3, 5, and 2, right? Those same prime sinusoids. But I also introduce a 15 hertz sinusoid. So they're overlaid, so they're coherent. They're all matching in phase. They're all phase aligned. And what you can see is wherever there are common factors, so a common factor meaning a zero crossing pulse from the 15 hertz wave, that's the number we're trying to divide, the dividend, and a prime divisor, that you'll get a little bit of an increase in amplitude here. So you'll see that a lot of these waves have a unit of 1. The waves have a unit amplitude of 1, and the zero crossing detection spikes have an amplitude of 1 too. So what you're doing is you're feeding all those spikes, those unit 1 spikes, into an analog computer. And analog computers can do this in real time, and they're going to generate a pulse of 2. Basically, you're saying, hey, I saw a factor between a dividend and a divisor, and so my amplitude, since I saw those 2 spikes at the same time, and I'm adding them up, I'm going to see an amplitude. So these are detected factors right here. This at the top, you can see the detected factors. Okay, so we're using resonance and there is adding, and there are digital computers here. Digital computer, a very specialized stripped down computer that does adding. Digital computers are still the fastest way to manipulate and add numbers. So just because there's an analog nature in this architecture, you're still using digital computing in parallel, doing the adding, adding the detected factors. So here's a picture of what the concept looks like. You have your computer filled with prime oscillators. Your oscillators tuned at prime frequencies and phase coherent and ultra precise. You have those oscillators there. And then you have your dividend that you're feeding into the computer, and this is your number that you're trying to divide, but it's represented in a sinusoidal as a sinusoidal frequency. So of course there's some challenges when you're trying to represent large, ultra large numbers. Representing those as a frequency is something it still keeps me up at night. It's like, wait, how am I going to represent an ultra large number as a frequency when modern computing, the highest we can go is, say, maybe 12 gigahertz or so. So there's some challenges there and some areas where I'm still figuring out things. But this idea is better suited for smaller numbers at the moment. Okay, so we're feeding in a sinusoid, and then we're getting out essentially like an interference pattern is one way you could think of this. That's the output. So we have 1, 2, and then 3 being the resonant detected or the common factors as an output. So as you could see, that computing, all those waves superimposed, in a superposition of waves, that it gets really busy, even though the computer is doing something pretty simple, detecting, detecting zero crossings. Putting those all together can be quite messy. It's a lot to mentally keep note of. So the result of one of those computations, these detected factors, would be like, if you're kind of interested in math, the fundamental theorem of arithmetic. Carl Gauss was the mathematician noted with he observed that every number has a unique prime signature. In this case, if we take the number 2420, I just came up with this example. If you were to factorize this number, it would be 2 to the second power. So there's a prime number 2 to the second power. It's 5 to the first power, which is 5, and 11 to the second power. So there are these factors that come out. And this is how the user interface would show the common factors in this architecture. It would show them almost like I don't know what to call this chart, but just, when you're sitting at your pen and paper and you're just trying to be creative and you're just thinking, how can you reinvent the wheel without, and leverage tools and imagination? Like, this is what I came up with. So it's almost like a little tallying type of display. And this would show what your factorized number would look like in a graphical form. So your computer's working on a number, and instantly that this chart displays because it's showing you those detected factors. Now, this is just a small portion of a larger chart. If you're doing larger numbers, you might have, here we have prime numbers 2 through 19, but you might have, much larger prime numbers. So your range might go a lot farther, or your domain, I'm sorry, the x axis would go a lot farther out to larger and larger primes. And then, as you can see along the y axis here, are your powers of that prime. How many times was that prime essentially like, how many times are you accounting for that prime? So in this shaded approach, you'd see 2, and then you'd see these 3 gray blocks. So that means that the computer detected the prime of 2, not 2 times. That's not the right way to say it, but 2 to the second power. So there, and then you can see also 5 to the 1 power, and then 11 to the second powers also. So just an example to show you how a factorized result would look. And the idea from this factorization result actually came a little bit from the FFT, and I'll show you why. So early on, even before ChatGPT, I asked a friend of mine. He's a respected colleague. I say, "Hey Jack, can you give me some MATLAB that would just generate a sinusoid?" And I gave him the sinusoid. Here's what it looked like. I said, "I want 2 hertz plus 3 hertz plus 5 hertz plus 2 times 7 hertz plus 11 hertz plus, I just wanted a sine of certain frequencies, of known frequencies. In this case, we have 1 hertz, 1, 3, 5, 7, 11, and 13. And I asked, could you do a FFT on that? And could you do that in MATLAB? And later on, I moved the code to Python. But this is like simple 2-line code. This is not hard code. I mean, I surely didn't have the insight into how to do it at the time. But I had a friend, help me with this. And the reason why I just wanted to confirm, which I knew, right? We're computer engineers. Some of us are computer people. I knew there would be a frequency spectrum, but I just wanted to wait a minute, is this going to show the result in the way I think it is? And of course it did. If you look at the frequency spectrum of this X function, if you will, this time signal function, the FFT or the Fourier transform is going to pick out those frequencies, right? So you have this time domain signal. You do it. You run a spectrum over it, and you'll get these. You notice there's the 1 hertz spike. There's a 3 hertz, the 5 hertz. And then you see the 7 hertz, but you see the amplitude is 2. That's because we added 2 in the original function, time-based function. We had 2 times the 7 hertz signal, and we have 11 and 13. So it's like, wait a minute, and again, sometimes I'm known for thinking myself in circles. So it's like, wait a minute, what are we building? Perhaps what we're building is a computer that behaves in the frequency domain. Maybe is one way to think of this computing method. Whereas today's computing is, of course, fetch and store and digital. Perhaps this computer is more of a frequency first computer, and looking at it that way. So I've been, again, this is a work in progress. But this shows how this factorization result is consistent with what you'd see in a Fourier transform breakdown, a frequency spectrum. So let's talk about precision, because again, this keeps me up at night. It's it seems impossible that we'd create a frequency representation of a 2 to the 256 power number. That just seems impossible. And I don't know how. So there is a hardware limit on this approach. And I've been thinking of how to solve that. But aside from that, this is a big part of the problem, which is picking out ever and ever if you remember your calculus class and you're doing limits and you're zooming in infinitely close to 0, or to that limit where their function approaches this kind of 0, that's essentially what we're doing here. But we're also embracing the reality that there is nothing such as absolute accuracy. There's a bounded accuracy. You can have accuracy within a certain bound, but you can never have absolute accuracy. So I wanted to embrace that and say, well, maybe we're not ultra absolutely accurate today, but what if we got better and better? This zero crossing detection. And so with this is showing a sine wave kind of crossing 0 and looking at what the errors would look like. So you'd have like this kind of vertical error, which I called mu. You'd have a vertical error, which is how close the sine wave is coming to 0 from a vertical perspective. And then you'd have like an epsilon. I called it epsilon, like what's the epsilon distance away vertically or horizontally from that 0 crossing detection. So the idea is to build better and better 0 crossing detections, so that when the energy of a sine wave, the electrons, the oscillating electrons, or whatever oscillating phenomena you're using in your quantum computation, whenever it gets within this threshold, that is what triggers the 0 crossing detection. So you'd have some kind of pre-detection, before the zero crossing happens, you have a trigger that says, hey, I'm detecting something's within our energy or within our bounds. And then you're also detecting when that thing leaves the bound of detection. Okay, so right here it's looking like a square pulse. And this surely would work for certain applications. If I had a detection circuit that could detect a square wave, that would work. But ideally, it would be like a Gaussian wave. And I have other kind of demonstrations of that. But this is just, I wanted to show this is the role of precision, is that the better precision you get, the higher frequencies you can detect, and the higher integers you can detect factors within. So in my thought process, of course, our thoughts are not linear. We're nonlinear thinkers, but for this presentation, I had to put it in more of a linear format. So what I had to do, and what I've been also kind of working on, is how to justify what I'm doing in using physics, using hard math, using how to relate it, not how to justify it, but how to link it to the existing mathematics language. How to, you don't want to be in an island. You want your work to meld well with existing math, existing theory, right? We have years of mathematics and physics, and it would seem foolish to just leave that all behind. You have to integrate with what's already there. So a qubit, we come to the idea of a qubit. And I don't have the equation of a qubit here, quantum state, a two-level quantum state. I'm assuming you guys are really familiar with that. So I'll spare you that little graphic there. But a complex number, you can use a complex number as a type of qubit. It has the properties that make it suitable. One, it has orthogonality between the imaginary and the real axis. Now, of course, in quantum, they're using the same mathematical definition of orthogonal, but they're expanding that definition, so you can have orthogonal being up and down, right? But if we go here, let's look at a complex number, and let's look at what a qubit might look like. So we have our A and our B. A plus IB, and that's our Cartesian view. And we also have this A, which is the square root of A plus the square root of B. So essentially, this thing's oscillating in a unit circle. This complex number in this case, if you can imagine, it's oscillating in a unit circle of amplitude A. So there's a little radius of A, and this energy, this oscillation, this mode is oscillating. And so here we have C equals A times cosine of theta plus I A sine of theta. And there's been a big kind of push at looking at quantum computation from an amplitude and phase control perspective. And that's good, but you can reframe that picture. Amplitude, and this is a little my opinion, my approach, amplitude can be noisy. When we're looking at those sine waves, if you've ever worked with electronic circuits, it's hard to control the amplitude of these circuits. Oscillator, you can control the frequency really well, but you can't really tell where the thing hits the amplitude and comes back. Like, that's hard to detect. But you can detect the zero crossing. There's a clear, that's distinguishable. The zero crossing is distinguishable. Even though the amplitude might be hard to detect, you might use, there's circuits for detecting amplitude, like capacitors that store the charge, a sample and hold circuit, but they're not so fast. It's like, but that moment of crossing zero, that's distinguishable. So one of the challenges I wanted to do was reframe the quantum qubit idea. In this case, we're using real complex numbers, away from the amplitude and phase, and reframe that in terms of frequency and phase. And that's why this talk is called frequency and phase control. So it's real simple, though. Right, the amplitude is a unit circle. It might be a unit of A or a unit of whatever magnitude you might have, but you can almost essentially normalize that to zero. So imagine the amplitude actually doesn't matter. The amplitude is what it is. But then what you do is you expand the frequency and phase variables. So we have for frequency, if you remember, phase is the angular frequency times the time plus some frequency offset. And so that's what this is leveraging. It's leveraging those frequency and phase variables because it's easier to distinguish that moment of crossing zero than it is to look at the amplitude. And so our equation goes from a complex number with using A for amplitude and theta for phase, to using A as 1. A is normalized away, the amplitude, and we're looking at more of the frequency, the angular frequency, and a different phase. This is a phase, and remember, we have a 1 hertz signal in this architecture. So we're using the 1 hertz signal is our phase, our absolute phase reference, if you want to call it that. So we have a phase kind of, there are actually multiple phases. There's a phase away from the 1 hertz signal, and then there's other small relative phases. And I'm actually working on some slides to, describe all the different phases that matter, because there's more than one, anyway. So, but I didn't want to talk about that and dilute the message. And here we're just using the frequency and phase is a phi. Okay. And also still went looking back for existing mathematics, and I stumbled across an oldie but goodie, De Moivre's theorem, which says that if you raise a complex number to a power, you're increasing its frequency. So I was like, ooh, that looks useful, right? So if you're taking a complex number and you raise it to a power, it's stuff we've learned. I'm assuming you guys all have learned this stuff, all right? Because we come from similar backgrounds, but it just gives a new kind of spin when you look at it in the terms of like what's useful. You're looking at old mathematics and looking for usefulness, and I thought this was really useful here. So there's that mode of oscillation, raised to a power. You're going to increase the frequency. So I thought that was useful. I also went back to monochromatic light. We all know, all here, right, that light has a speed of propagation, and we all know that number. It's a constant. It's that 299,792,458 meters per second. That's the speed of propagation of light through a medium. And of course, the medium, that speed might be affected by the medium. When I say medium, I mean the permittivity, the permittivity and permeability constants. Those constants will affect how this energy propagates through the medium. But we all know that light is lambda times mu, lambda being the wavelength, complex wavelength, and mu being the complex angular frequency. So creative mode, often you go into creative mode and then you come back and you check whether it's sane. But I thought, well, wait a minute, and it intuitively makes sense. Light is not one frequency. Light is it can have color. We all know light can have color. And what is color? Color is the superposition of those frequencies. We also know that you can send light through a prism, and the prism separates those colors of light. So right, so the colors are like these independent superpositions in light spectrum. So I thought, what would that look like mathematically? And to me, it looked like this. And I say to me because a lot of you guys are well experienced, and I did, I'm still learning this stuff. So, but a reframed light instead of a constant, we're looking at light as a variable. And not a variable speed, but a variable of frequencies, a superposition of frequencies. So that's what that looks like. This lambda nu, so you're taking all the distinct modes of frequencies all the way to the nth mode or the nth frequency, and you're superimposing them together. And another interesting thing pops out is that you can actually reframe this in a Dirac notation, where you have your vectors, your lambda vectors to the left, and you have your mu vectors to the right. right. So that becomes possible. So it's like you're storing information in the components of color. You know, that's the information. The information are the resonant modes, those oscillating modes. Like, whereas digital computers, the information was the voltage or a yes no, a digital value. In a quantum computer, the information is the mode of oscillation. Like that's what we're manipulating and trying to store and trying to recover and all that stuff. So I, went back and looked at physics of light, optics, and things, and just check for continuity there, see how that fits. And then I know we're all familiar with the block sphere. The block sphere is a representation of a quantum state. Often that quantum state is fixed, so it's like, it's an arrow, it's a vector, pointing in a fixed direction. But in this model, and I'm going to show a sphere on the next page, but it's actually carving a path, if you will. That's a better way to describe this quantum state. It's a state that's carved over one period of, relative to a 1 Hz wave, right? It's a mode of, it's a pattern. It's a state. States generally have motion rather than just a fixed state in an arrow in a direction. So what I try to do is say, well, what if lambda were a complex number moving, that one axis, and what if I took the nu, lambda and nu? What if I took nu and that was an orthogonal? I made nu orthogonal to lambda, but they were both oscillating, in their own respective phases and whatnot. What would that look like? What would the projection sphere look like? And this is what I came up with, is that the sphere might look something like this. We have these two complex numbers projected orthogonally onto one another, and they're producing this kind of projected reference point, this projected vector. So this is one thing I'm still playing with this, and the closest, if we're all, if you go back to your analog engineering, the Lissajous figures, come up here. You can potentially use a Lissajous figure to represent a quantum state. It's possible. I'm not sure yet. I'm still reading and researching, but that might be a way to represent this quantum state, is using a Lissajous figure. For those of you who may not be familiar with the Lissajous figure, you're taking an analog oscilloscope, and instead of plotting time over the voltage of your signal, you're taking one voltage of a signal as the X and another voltage of the Y. So you're taking two voltage signals and displaying them, on the X and Y axis, and you get this kind of interesting figure. So if we keep going, okay, minimum viable product. And I saw a question below that says, do you have physical hardware to implement these operations? Well, here's what I think it would take to produce this, what we're talking about. Minimum viable product. Okay, and I've been reaching out to manufacturers and things like that. And, of course, electrical equipment costs a lot of money, scopes and triggers, and it's a lot of money. So if there were funding raises, here's what it would go on. Okay, first you need precision oscillators. I mean, precision is relative, but you need some oscillators that are, better than I could create on my desk, right? So there might be some test equipment there. And I've reached out to some respected electronics company and gotten some quotes. So precision oscillators are one component of this. You do need some type of feedback. You can't just let an oscillator free run. It's going to go out of phase. We all know that, right? You're going to let it run, and as precise as it might be, it's going to lose coherence after some period of time. So you have to have, in my estimation, you have to have some kind of phase lock loop control and feedback on that oscillator. You have to have a way to tell it, nope, no, get back, stay within the error, right? It has to stay within the error, or else the thing will lose coherence and slip, and just a messy thing. You have to have control. So you need oscillators, you need some kind of phase lock loop control and feedback. And some of you may know there's a frequency and phase lock loop. You need that one. You need one that can maintain coherence with the frequency and phase, not just a phase lock loop. By there are different versions of PLLs. You need one that has frequency and phase. Of course, you need this zero crossing detector. You need this circuit that when you put a sine wave through it, it's going to generate the pulse that we need. There's some innovation that needs to happen there. And then also you have to do the actual combinatorics. You have to do the counting, the mathematics. So you do need digital up counters and down counters, specialized little circuits. And then you need like registers to hold those values. So you need some digital registers and perhaps some shift registers too, because we're taking a number that's represented as an integer, and we might be shifting it in so that we can represent it as an oscillator, right? I don't know exactly how that's going to work. I'm still noodling on that part. How are you actually going to take the digital number and shift it so it's an oscillation value? Still working on some of this stuff. Then you also need you need analog computer elements. So you need summers, mostly summers, but you do need analog computing elements, op amps, precision op amps that are wired for analog mathematical operations. And then lastly, some pin diode switches. There's a really cool video on YouTube where the gentleman is describing a pin diode switch. It's a switch that you feed an oscillating value through it, and it'll block that value. But if you apply a bias voltage, it'll let the sinusoid value pass through. And I thought, that would be kind of cool. Like there's a way to control whether this sinusoidal value propagates through your circuit. You need something like that. So these are the parts. If these parts arrived at my doorstep, I'd go to town wiring them up. And here's another realization. Some are using light for quantum computation. Some are using ions and technology that I'm still learning. But they often say some of the path forward comes through constraints. And I think that's true here, because at first I had the ideas and they were like light based. Then I started thinking, I don't have access to light. I don't have, prisms and dichroic materials and light, and they're bulky and big. I'm like, how can I make this work right now? And the realization was that light is on a spectrum. Light is on an infinite spectrum as we know it. So if that's true, you should be able to design a low frequency, like start at 0 hertz, 1 hertz, 2 hertz, you should start with something that is tangible, available, useful, and you could start at the lower frequencies. So that's what this is doing. So this came out of constraints, going low frequency instead of having higher frequencies. It's like, hey, let's demonstrate quantum effects at the lower frequencies and then make it our goal to go higher and higher and higher. Like that would be almost like that Moore's law. They didn't start out doing 1 nanometer nodes, right? They started out with what they could, and they endeavored to get better and better. So I wanted to note that, there is an awareness that we're operating in the lower frequency spectrum, and and perhaps it doesn't matter. You start where you can and you aspire to do better. Okay, so those are some minimum viable product parts. Here's what the processor might look like. I've been calling it desynthesis. I don't know, it just sounds cool. Desynthesize and synthesize. So desynthesis is a process of taking a composite number, a prime or composite number, C, turning it into a sine wave, and then decomposing it into its primes. So desynthesizing a number, taking a number and splitting it into its basis states, if you will. So this processor might have one input. The input could be a digital number, or the input could be the analog wave itself, but you have to get the information in the computer. And then you would have a series of channels as outputs. See, these are prime, you have your 1 hertz output. I just did that for good measure. I don't know that that's necessarily useful yet, but for good measure, we have to have the 1 hertz reference output. Then we have the first prime, the second prime, the third prime, all of our primes up to our system state capacity, which is the nth prime. So we might have quantum computers that, whereas digital computers are 32-bit, we started at 4-bit, we went to 8-bit, we had 16-bit, 32-bit, 64-bit, and right. So your quantum computer might have a finite number of prime states. You might have, you know, 13 states or 16 states. You know, you're going to have some finite limit to the number of primes that you're analyzing. So there is some kind of finite limit here that I did want to, you know, mention. And so your processor, let's go one more slide. Your processor, this shows a little bit of a better picture, and it's showing the fundamental theorem of arithmetic at the top, where n is some number, and it's a product of primes to their respected factors. And that's the mathematical view, and the computer view of that would be right below. So we have the same desynthesis processor, but the outputs would be, so if we detected, you know, so 2 to the second power, if we go back to that picture we showed, we had 2 to the second power. That means on the 2 hertz channel output, on the physical output channel, we'd see a wave of 2 hertz. That's how you'd represent that. I hope that makes sense. So we had 2 to the second power. That might mean that there'd be a 2 hertz signal coming out of that channel, and then we had 5 to the 1 power. So there might be a 1 hertz wave coming out. I'm still figuring this part out, but the idea is that the exponent would be represented by the sine wave on that particular pin. So you'd be able to kind of immediately look at each pin, look at how it's oscillating, and you'd know, well, this is oscillating at 2 hertz and it's on the 5 hertz channel, so that must be 5 to the 2, right? So we're decomposing it and trying to use physics, you know, exploiting physics. Okay, so that's what that looked like. Now here's the architecture that is published. It's now published by the USPTO. And we have several variations of this chart. You know, I'm working with the IP lawyers, and you know, we have a few different versions of this. But this is kind of what I think the architecture would look like. And you know, what always keeps you up is like if you forget something, you're like, oh, I forgot a block. So that happens. It's like, did I forget to include something in this chart? And probably so. You know, but you just have to keep taking steps, you know, in development. If you're doing R&D, there are those moments where you're not sure of yourself. So you just have to keep taking the next step. That for sure resonates. So here's where the current, you know, here's the current architecture. Right now, you know why we have the lambda and nu. That's from modeling the polychromatic light. The speed, you know, the speed of light broken down into components. That's where that lambda nu, that's where those are coming in. And so in this computer, each channel, you have to, there's a phase adjustment, and I'll explain on a later slide why we have to do phase adjustments. And then you have that channel. So there's an oscillating voltage or an oscillating current. You can use current mode oscillations, which actually might be better, you know, having current oscillations instead of voltage oscillations. So, but you do have an oscillation in this channel. This channel is some type of impedance controlled because you want to control reflections and all those good engineering practices. But what this is attempting to show is that each mode of oscillation is fed into a zero crossing detector, the phase lock loop that we talked about, and then some kind of analog processing, those blocks, those processing blocks. And on the left-hand side, you'll see we called it a programmable gate array. And at the top, it's called programmable gate array. Now, we all know there's a field programmable gate array, right? FPGAs. But I took the field out. I didn't want to call it a field programmable gate array because those are digital, and those have a very specific meaning. I wanted to leave it open for another type of programmable gate array that I might not know about at the time of writing. So in practice, we might use an FPGA to do some of the processing, some of the detection, but not all of it. And as some of you may know, there are analog processors too that are out there. Some I'd love to get my hands on and play around with. But so programmable gate array, there's the oscillator creation, which is 300 in this picture. Those are the oscillators. and there's some phase control to keep it coherent, and then there's the the processing that happens off to the left hand side, and then there's the recombination of the signal and output of the signal at 1000. So this is the best picture that I have so far of what something like this might look like. And now let's go to the practical side of things too. The quantum advantage. Now, some of you may know there was a recent contest. Google had a contest. I applied for that. I didn't make it past the cut, unfortunately. But here's a picture that I created from that submission. It shows like the theoretical. If we take this approach that I've been sharing, if you have an appropriate large number and you have the appropriate number of oscillators, then it should be that we can factor a number in the period of a 1 hertz, in one period of 1 hertz sine wave. So if you're thinking computer science and worst case analysis, that O notation, it should be O to the 2 pi, which I know is unconventional. It's different. We don't have anything that's relative to waves. But that's the closest thing I could think of, that the time, the factorization time, the worst case time, if your numbers are within those bounds, your divisor and your factors, then you should have a constant factoring time. You should be able to factor a number in a constant time, and the time again is the time of a 1 hertz wave, one complete cycle of a 1 hertz wave. And the reason why is because you're doing all the zero crossing detections and you're doing all the digital counting in that 1 hertz wave, and then you're doing it over again and over again and over again, right? You're doing this computation really fast, but it's really repetitive. So you should have a 1 hertz. So the red line is dotted. That's showing what the quantum computer could do. Now, of course, it's really slow. It factors numbers in 1 second, and I am looking at ways to speed that up. And I've found some leads. There's some Chinese Chinese remainder theorem, and also maybe some signal compression, Lorentz transforms you can do. It's still a bit theoretical, so I didn't want to talk about it here, but this is showing what I did is I took my computer, my laptop, and I used some chat GPT. I said, hey, generate me just repeatedly factor numbers using basic trial division and generate me a plot. And this is what my computer did. It chose higher and higher numbers. So we chose from 20-bit numbers all the way up to 50-bit numbers. I had it do randomization and I tweaked it a little bit, but this shows the time it took to factor those numbers. So you can see between 45-bit numbers and 46-bit numbers, my computer was starting to hit that 1 second threshold. In other words, 2 to the 42nd, 45th, 2 to the 45 size number. My computer was starting to, do it, factorize that number in 1 second at 2 to the 46 power. And then at 2 to the higher powers, you can see they're clearly going beyond. The computer's taking more higher than 1 second. So I call this the inflection point. Now, keep in mind, if you're on a supercomputer, this chart's going to look different for every computer you're on. But I just wanted to get an idea, like where would a quantum computer that could theoretically factorize a number in 1 second or a constant time, how would it, where would that break-even point look like? And this is where I arrived at. There might be some errors here, so I apologize. If you guys see some glaring errors or, like, hey, no, that's not right. I sincerely apologize. It hasn't been peer reviewed or anything yet. So, but I established some kind of chart to look at what the scale would look like. And of course, this scares me too, because it's like, I don't know how to generate an oscillating number of 50, 2 to the 50-bit, that number is really high. The chances of turning that into an oscillator value are slim to zero. So, there's a little bit of a moonshot for sure. The moonshot is really strong in those higher bit numbers. So it almost feels comfortable to try to just see, I can't see the future that far, but I can just do what I have right in front of me, which is just, does this work at smaller numbers? just start there. And then sometimes you talk to people who can think of better ideas and take it further. So that's kind of where this is, from a personal endeavor of R&D. It's certainly like you look far and it looks really hazy, but it's like, you know what, let's just start here. And so another metric is for a given size number, for a given size integer, how many oscillators do you need to factorize it? Worst case, like if you had all the primes, how many primes would that be? How many oscillators would you need? And then comparing that against the trial division. Trial division is supposed to mean if you had a basic computer and you just did repeated division to try to divide the number on a modern day digital computer. That's what we're calling trial division. There are division algorithms out there that will optimize division and do things faster. But I just thought, how would this compare against a trial division? If we had oscillators. And this is one of the charts that I generated. So there's a potential for faster, more efficient computation. And more efficient, you have to, right? Efficiency can mean the power, right? For the same power, does this computer do it differently? There's time efficiency. There is, circuit efficiency. There's all these different efficiencies that we can look at and try to see can quantum computation be more efficient than the equivalent digital way of doing things? And there's hardware resource efficiency, right? So it opened up a little bit of a Pandora's box in terms of efficiency. But I tried to say, well, what if an oscillator were the unit of, how would that scale? And this is what I got here. You'll also notice that this chart is limited to 15 bits. So even though in the previous chart it was, 2 to the 50th bit number, again, I realized that's not so attainable in the near future. So what if I cut down my goal to 15-bit numbers and then generated the chart? So this is a little compromise chart here. So let's switch, so I think now you understand the concept that we're taking sinusoids represented by integers. We're using zero crossing detection. We're aligning those sinusoids. They're on separate conductor paths, so we're aligning them, and we're looking for resonance, modes of resonance. That's the concept. And I've been calling it wave-based computing. It's not technical. I mean, it's a type of quantum computer because it uses waves for computation. But in the patenting process, one of the scientists proposed, why don't we just call it wave-based? And I thought, oh, that's great, because it gets me out of calling it a quantum computer, but it's still doing wave-based computation. I was like, oh, thank God, And also, I like the name wave-based because it's not so flashy. It's very practical, and it has meat on it. There's meat on those bones. So let's look at, just for a second, some of the other applications, right? We all know particle wave behavior. Right, particle wave behavior. In other words, when a wave hits a wall, or when a wave, if you're mechanical engineering inclined, when a wave hits a medium, if you're electrical engineer, when a wave hits an open or closed circuit, there's something that happens at that medium. We all might know it. There's reflections that happen. And in my opinion, that's the core of quantum computation. We're going to be hitting things with waves, analyzing the reflections and inferring about the thing itself, that thing being the wall. If you hit a wave at a wall and it comes back at a certain reflection, without touching the wall and going and looking at it, you can tell whether that wall was open or closed, or right. So you're kind of doing this remote sensing. And in my spirit, I think that's like a pure application of quantum computing, is bouncing waves at objects, measuring reflections and rotations, and inferring something about the thing that you bounce the wave off of. I mean, that's how stealth works. In fact, stealth is looking at reflections. So we all know that when a wave hits a medium, the medium absorbs some of the energy, it reflects some of the energy, and it also transmits some of the energy, or emits emission. There's spontaneous emission. So transmission and emission, I kind of group those two together. And this chart is showing an example where you have an original wave. This is there's a trough and a bit of a peak. And I made the peak a little bit higher than the trough so you could see the symmetry. So when this original wave hits a boundary condition, it gets reflected. And this is one type of transformation where you just invert the phase. The wave is coming back the same way it's reflected in the x direction, if you will, along x. That's one type of reflection. There are other reflections, though. You can have a rotation, a phase rotation, so where your original wave hits a boundary, and if that boundary is opened or closed based on the state of that boundary, the wave will come back but reflected. So in other words, in the second example, the peak, see the peak is high and it's at the top when it's incident, and when it's reflected, that high trough is reflected like 180. It's a type of 180. And this, I think, this is where the Bloch sphere and rotations, I think, are relevant. In other words, the Bloch sphere, or whatever type of sphere you decide to use your convention on, this is where the x, y, and z rotations and all that stuff have to play, right? Because you're representing a wave and you're looking at the reflections as it comes back. So in the last example, this third example is like a simple phase shift. I think we're most familiar with that one, where you have a wave and it hits a boundary and then it gets phase shifted by some amount. That's the third. So there are all these reflections tell you something about the thing that you can't directly observe. And I think that's a really cool concept. And it's, again, that's the foundation of stealth, where you're looking for the presence of reflections to tell you if something's there. But if you take this wavelet switched networking idea, here's one more theoretical slide. There's a practical slide coming up. What we're going to try to do is represent a computing node as having multiple states, and we're going to call it a quantum object. So we have this object that has these prime states, and they're oscillating. And what we're going to do is conceptually, we're going to hit this computer with an incident wave, and it's going to respond, meaning give off reflections of a certain type. That's the concept. So you're going to have a wave-based computer. You're going to hit it with an incident wave, almost like the photoelectric effect. You hit a material like metal with light, the right frequency of light, and it responds by emitting electrons. So it's a type of reactive computing. But in a wavelet switched network, this was a picture to try to show you that, but there's really this picture. It's like, how do you build something that responds like that? And this is the closest I've come. Again, using off-the-shelf parts, like things we can actually go get right now. So what this is showing, I apologize, this is from the patent application, but what this is showing an incident wave coming in from the left. Now, it just shows a sine wave, but imagine it can be a wavelet too, like a little envelope of multiple frequencies. It can be a modulated wave as well. That enters the system at what the label is 1501. There's an impedance. That's really 1501 is like impedance matching, circuit. So that, you want all of the energy of the wave to come into your circuit or not, depending on what you're designing this for. But 1504 is something we're all familiar with, RF circulators. If you guys work in the RF field, radio frequency field, there are these things called circulators, and they're usually 3-port devices. They have an input, and they're used to isolate, transmit, and receive. So that's what this is doing. You have the RF circulator. Essentially, a quick description, what comes in as circulator on pin 1 comes out of pin 2. What goes into pin 2 comes out of pin 3 or port 3. And what comes into port 3 comes out of port 1. So there are these little merry-go-round structures where you're routing information through a circulator, and that's exactly what this is. So your incident wave is coming into the circulator, and let's say we're just trying to model a reflection. We're trying to build a quantum object that can reflect. It's simple. You would think, why do we even have to build that? You can just reflect by creating a medium, but you want a computer to simulate this reflection. So we have the information going in the form of a wavelet. It goes into the 1506 block, gets decomposed and analyzed. It gets passed to the 1508 block. Again, this is analog energy, waves. These are waves going into your system, going through your system, coming back out of the system from 1508 back to 1504, and then coming out as a reflection. Like that's one way the energy would get routed through this network. Another way the energy might get routed through the network is, again, we come in through from the left, we go into the circulator, the RF circulator, we come out of the circulator at 1510, and then we go out of the medium at 1512. So that could be another mode of the example for that is the particle slit experiment. With the dual slits, you have light going, or you have a wave. It can be light too, but you have a wave, electron beam, or going into the double slit. That would be that would be coming in from the left hand side on this chart, and then we have the waves exiting the double slit. That might be the 1510. That's an example where it's not just getting reflected and coming back, like it would be if it were coming back to 1504 and coming back out. It would be getting affected. There's a transform that happens, and you're outputting the resulting wave after that transform. That's what, and that wave is leaving on the right hand side. So this little networking node is taking a wavelet, routing it, analyzing it based on like work functions or some kind of threshold or pin diode switches, and then outputting the results. And I called it wavelet switch networking because in computer networking, we may all know, in the academic sense, there are circuit switch networks. These are networks like the old AT&T networks where you called a switch and they literally took your physical cable and moved it to another port, right? Physical switching is one way to route information. Then we got we got packet switching, right? In modern day Ethernet or IP-based networks, we have information that's switched based on the digital content, the source and destination, and routing. Switching happens that way. So I called this wavelet switched because you're switching the path of your wavelet or your pulse of energy based on the frequency components in that wavelet. So it's a wavelet switched. So if you do develop this simple concept, you have some circulators, you have some processing in between, analog processing, and you have some impedance matching nodes on the ends. If you take that I don't want to call it a simple concept, but if you take that fundamental concept, that unit atomic concept, you can scale it up. You can take one reactive computing module, you can connect it to another reactive computing module, and you can let them talk to one another, so to speak, right? One will talk and the other will reflect and emit, and there'll be this exchange, if you will, for lack of a better, there'll be this interaction between them, and the interaction will be based on what you program those nodes to do. It's I don't want to get too abstract here, but it's like when we notice humans have multiple emotions at the same time, and those emotions can be layered. So you can be looking at someone and they can tell you something like, hey, get off the wall, or something. You're talking to your child, hey, get off the wall. But you could say that, get off the wall, or you could say, hey, get off the wall. The energy or the emotion that message has when it carries the message can influence how the receiver perceives that message and reacts. That's the best analogy. So think of each of the wave states as maybe an emotion, and you can have systems that are designed to maybe react to the emotion of anger more than the emotion of, so and so. So I'm using that as an analogy, just the emotions, because we humans are particles and we use waves to communicate. It's, that's pretty well known. It's not used in physics a lot, but it's well known. It's how we interact. And similarly, in these systems, you have a wavelet containing one or more frequencies. And the receiving system would perceive those frequencies, which means pick them out, discern them, and then react appropriately as it was programmed to do. So that I call that reactive computing. And here's another chart of the reactive computing model. You may be able to simulate modules or something using this kind of back and forth concept. And that's it. That's what I had for you guys today. I didn't go for the full 2 hours, but if you are interested in learning more about or reaching out and contacting, I'm all about learn by doing. So yeah, I'd love to get to work. Here's my contact information. Our website, my website is on my to-do list. So it appears to be down, but we do have the domain. But I did put some energy into a dynamic search, a small business, DSBS, the dynamic small business search. And you'll find me there. Yeah, here's my cage number if you're into government contracting, and my email address. So I'd love to hear from you. Again, mentorship, steering the ship. Maybe there's some course correction I could do, or there's some technical feasibility, and we can demonstrate and prototype this thing, show it works for small integers. That would be ideal right there. So I thank you all for allowing me some time to talk and share with experienced people such as yourself. Thank you very much.
I noticed a question from Dave. He asked, do you have physical hardware which implements these operations, or is it theoretical at this time?
It is still theoretical, meaning there is no, like in my lab, I don't have a circuit yet to plug it up and try it out. I have simulated though. I've used Desmos graphing calculator to simulate the resonance. So that's more of a software model. I think the question is like, do we have some real hardware to really test this out on? So not yet, but I have reached out to, let's see, I've reached out to Zurich Instruments. They make precision oscillators and control equipment. It's expensive, so I'm not opening the pocketbook yet, but so I've kind of lined things up, and the longer I go without, say, being funded directly, the more I just kind of flush things out mentally. So when the resources or funding does come in, I know how to spend it. So to that question, I think the closest thing in terms of, if there were some type of parts, they would look like this list, this minimum viable product list. Some oscillators, preferably tuned at prime frequencies, frequency and phase control circuitry, zero crossing detection, some up and down digital counters. These can be discrete components, digital registers, analog computing elements, and pin diode switches. That's what I would, I think that these parts would get you to a proof of concept. So thank you for that question.
And also, I noticed Terry Bollinger, he has a lot of comments on the chat. So Terry, can you unmute and talk about your feedback?
Yeah, Lytle, I like a lot of what you're trying to do with this in the factoring point. I think the interference idea is definitely gets an idea of where there's natural factoring in history. You also point out the resolution issue, and I think that's going to be the big issue for scaling this up beyond certain things. As those frequencies get higher and higher, the resolution between them becomes extraordinarily difficult to maintain that. So you wind up with having to have a very long wavelengths in order to get the interference effects.
Yeah.
So, but the idea that you get the interference with this using these waveforms, again, that's spot on. I've made several comments. Have you ever read the book QED by Richard Feynman?
No, I've heard of it. No, not
Oh,
yet.
you should absolutely should read that. I think you would immediately resonate with some of the features in there. In the chat, I put in one figure that looks just like one of your figures from Feynman's book, where he shows interference between red and blue light.
Awesome.
And specifically, when Feynman's talking about that, he's talking about the iridescent color. This is on the front cover of his book. The iridescent colors you get from an oil sheen on water is actually an example of the kind of interference you're talking about, because the different light frequencies all interact, and some of them pop out and some of them get suppressed, and you wind up with these beautiful colors that reflect back from that sheen. So Feynman has a lot of things I think you would find very very interesting and relevant to where you're trying to take it with this.
Thank you for that. That's perfect. I'm a fan of Feynman's work. I've heard him talk in various lectures, and I know he was envisioning a computer that would
Yes.
work differently, and a lot of what he says resonates too. Especially when you come back at a problem, you can't solve it, you go to sleep, you come back, that kind of that resonates.
Try some new ideas out. Yes.
Yeah. So thank you for that.
Jordan, you have a question? Please feel free to raise your hand and ask.
Well, first of all, hello from California, Lydell.
Welcome.
And I want to applaud you for pursuing this. And I knew someone was going to catch on to this eventually. And there's two areas I would say to look into that could be helpful. One, on the scaling side of it, the dielectric boundary conditions. There's been a lot of work over the decades in this area that I think would help, and look into some of that work there. And on the other side of it, on the foundational level, there's been so much work in the digital audio processing. So think of audio engineering, and there's a lot of similar concepts that they have done, have really, expanded upon, that I think could have value in this. When you look at some of those concepts that they have done with look-aheads and dealing with parametric equalization of those frequencies coming in. There's very similar things going on there that I think is worth taking a look at. Absolutely. And thank you. This has been great.
Awesome. Hey, thank you very much, Jordan. And I agree with what you're saying. It's almost like the synthesizer, if you want to call it that, is a type of quantum computer, in that it's splitting apart frequencies and you're doing operations and things. And some of the I've been looking in that realm a little bit, partly because the frequencies are still in the lower range and the audio components work there. But even certain things like gyrators, they're this circuit that you can use to create synthetic inductors. Inductors are are heavy and big and bulky, and so audio engineering has used gyrators to create synthesized inductors to get the oscillation. So you're right on there, and that little head nod to continue that is powerful and well taken too. Yeah, thank you.
Absolutely.
Lydell, if I could point out another issue in this, when you mentioned Feynman's computing, he has a wonderful little article where he talks about his definition of quantum computing. And if you get into that, one of the things that's a little bit different from a pure waveform is this issue of entanglement. And there's different ways to present the entanglement issue. One of the ways that I usually point at is just the idea that you only get one photon, even though the photon interacts with all sorts of things. It only produces a single result, and that implies some kind of connection. Einstein really did not like this. Yes. It implies some sort of connection between all those different parts of the wave function and the instantaneous spot where that thing comes in. There's a lot of the power in quantum comes from the wave side. Entanglement is an issue that you might want to look at a little more closely in terms of whether you can, I do think there are ways to emulate entanglement in room temperature systems using photons, because photons do it all the time. They have to. That's how we can read what we're looking at on the page right now. If our lenses could not do that for each photon, we wouldn't be able to get the images that we see. So it's a room temperature aspect of both quantum computing and the entanglement. So you might look at that a little bit, not to the exclusion of looking at the wave side, because I think the wave side is more tractable in many things. But when you talk about like the qubits, qubits quickly get into some of the entanglement issues. They're less powerful when they lack entanglement. They do things when they do have entanglement that they can't do classically. So, which was Feynman's whole point. That was just saying that there's just things that just go, not just they just go hyperbolic. I don't know if exponential is the right term. It just absolutely blow up in trying to emulate them if you don't have this strange connection that you have between the wave and the particle representations. So some interesting issues. One other thought, you're doing small, I think you could get together small factoring systems fairly easily. I don't know the literature, I'm not familiar with it, but I'm sure there's some kind of literature about doing large factoring based on small factoring and how you could combine those. And I would assume that, by the way, that's an intense body of literature. That's one reason I'm not up on it. So even if you have very rapid small factoring, there can be some ways where that could work out into large scale factoring. And of course, as soon as you get large scale factoring, people get very interested. So that might be another approach is modularity and maybe how you can stitch these things together to give something that's more powerful without having incredibly high resolution that you would need for a direct computation.
Awesome. I appreciate that. I appreciate all this feedback. The closest I've come, and I'm still reading this literature too, is there's something called the Chinese remainder theorem, where it uses it basically, it says you can figure out what a number is based on the remainder of the remainders of certain smaller divisors, so you're using, so you have a large number, but you can divide it only by smaller numbers, smaller prime numbers. They have to be prime. There's some mathematical constraints. They're saying that you can reverse figure out what the large number was. And that solves one of the challenges I have, but not, it solves some challenges, but not others. So I'm still figuring that out. Like, how can you take something small and scale it up? That's still, again, keeps me up, meaning I haven't figured it out yet, but there's still some more literature to read there.
It's interesting. There's also a certain warning. I said that this is a massive literature. One thing you don't want to underestimate is saying, if I just solve this problem on my own, how would I go about doing it? My example I always love to give is the guy who came in late on Friday class, late for class. The teacher had put his usual example up on the board for the students to solve over the weekend. And he took it home and said, man, this is hard. Boy, this is a hard one.
Yeah.
And it comes back in, hands in homework on Monday, and the teacher comes back just sort of dumbfounded. How did you solve this? I said, well, that was a homework. He said, that was an unsolved problem no one's ever solved.
Right.
So we underestimate sometimes how we could take something just by saying, how do I make it work? And so I like your focus on saying, how do I make this work? So it's kind of the counter where I said you always want to know the literature, but you also don't want to get lost in literature because the literature will always tell you this is the only way to do it.
Right.
And a number of great insights on data compression is another story, same thing. Literature said it was impossible to compress the data beyond a certain point. A couple of engineers didn't know that, so they went ahead and did it anyway. And what they did is they took in the time dimension. And once they took the time dimension, it was the foundation of every compression that's used nowadays. So interesting insights can be there right in plain sight sometimes, and we don't see those. So looking for the insights and knowing the literature is kind of a little dance you have to do. You have to know what's out there and what's been done. But you also don't want to lose the drive and say, what can I do?
That's right.
So
that's right. That resonates. What you're saying resonates a lot because, like you said, knowing the literature, so we're not naive,
right.
but also allowing yourself to have that not be constrained by what you read. Like, oh, they say it's not possible. Oh, it's not possible. You still want to have that kind of that childlike ignorance or naivety to just go off and play, so to speak.
And I love that because literally some of the foundation concepts of the technology we're using right now, like some of the data compression, were done that way.
Yeah.
They just didn't know it. And technology also can provide opportunities that weren't there before. That's a common story. Packet-based networks could not do stream packeting because it was impossible computationally until it wasn't. And it took a small company to suddenly figure that out and say, we can do this now. And everybody else was just sitting there going like, oh, you can't do that, can't do that, can't do that. And these guys just jumped in there and did it. I love that one. That was a small company I interacted with. And when I realized what they had done and how they had done it, it was just so much fun because they realized, oh, times change, technologies change, possibilities change. So that's another driver. They can open up new ways of solving a new problem.
That's right. There's a quote by Einstein. Maybe he's attributed as saying, you can't use the same thinking to solve if you have a problem, you have to use a new type of thinking, and that really resonated. It's like, well, maybe factoring numbers is impossible because we're using it on the machine that we're using to articulate the problem. Maybe we need a different computer or a different machine altogether to solve the problem. And with the PN problems, the type, factoring is considered one of those non-deterministic polynomial problems. And but if you read the fine print, they just say that in order to solve one of those problems, you need to finding a factor of a number and verifying that it is a factor are like two different things. You need to just be able to verify the factor, and so there's some interesting wording there, which made me think, oh, so you're saying, well, we just need a computer to, given a number, just say, yep, this is a factor like that, and you need to do that faster than a computer. It gave me a little hope because it made me think maybe a new computer, and maybe we don't have to, maybe there's some shortcuts to get to the factoring problem that could, a fresh approach might work.
Yes. And fresh approaches are, another reason they're good is the example, this is for my last talk about it, but I love the example. Methane molecule requires, for a crude quantum estimate, crude quantum model of the wave function, requires more energy than existed in a year in the world. Well, that's funny. The methane molecules don't need that much energy.
They're here right now.
So something's going on there, and we make our own problems harder sometimes. So if you say, well, it has to be a digital solution with the following precision, blah, 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 you automatically assume all sorts of things, that you have to do it with bits and that you can't do it some other way. And clearly methane molecules don't do it that way. So sometimes we should look at it. They clearly are using a more wavy approach, that it's not one that, we can model it with digital, but it eventually becomes impossible. Right. So I like your thought of, look at different ways, look at different methods.
Awesome.
So do you have any other comments, feedback, or questions for Lindell? So far, I don't see any question on YouTube.
Thank you for the comments. I'm seeing those. I'm capturing. Will I be able to access these comments after the chat somehow?
Yes, I can send you the chat after the recording is done.
Okay.
Or maybe you can send me the slide. I can forward to the participants.
Okay. Yep. I have some slides ready for you all. Awesome. Thank you.
Yes. So is anybody having questions, comments? So I hope it's a pleasure to invite you to give such a great talk, and I hope you come back to us to give another talk next year.
Thank you very much. Thank you all for your time and for your ear. If you welcome to email me, reach out with any tips or nudges in the right direction, and I appreciate your time. Yeah.
Sure. So next week we'll have Terry Bollinger next Saturday, noon. So if not, thank you for coming. See you next time.
See you next time. Thank you.
Thank you, Lydell.
All right. Thank you very much, Terry.